The next test is called test of independence. And this is also a chi-square test, and it is used to test whether two variables are independent or not. So for example, you can have a situation where you want to test whether the wage rate is independent of gender, or is smoking independent of age group. Is there a relationship? The choice of major, like in college or business, is it independent of the racial grouping of students? So these are some examples of when we will use test of independence using the chi-squared distribution. The hypothesis is very easy to state, and the null hypothesis is always that the two variables are independent. The alternative is that the two variables are not independent, or you could say they are dependent. You can say they are not independent. That's another way of saying it. Here, to test the hypothesis, we have to take a sample and organize the sample values in a two-dimensional table. And this two-dimensional table or two-way table is also called contingency table. Okay, contingency table, we'll look at an example of what that contingency table will look like. So you have two variables. So you list values of the first variable as rows and the values of the second variable as columns. So then you look at how many observations from the sample fall into each of those categories. So value 1 and value 1, or value 1 for variable 1, value 2 for variable 2, and so on. So here there are n possible values for variable 1 and m possible values for variable 2. So you look at the sample and arrange them in this fashion. So now if you sum the frequencies of each row, that is the different values of variable 1, then we get the totals. And here we will use this notation T followed by two subscripts. First subscript is row, the second subscript is column. So the row subscript is 1, the column subscript is dot. So that means this is the sum of row 1. This is sum of row 2, or T stands for total. Total, row total for the first row, row total for second row, and so on. And here if you sum by column, then you get T. The row subscript is the dot and the column subscript is 1. So this is total for column 1. Okay, so this is column total for column 2, and so on. Now the total of all of the frequencies, or grand total, is T. And you could compute T by either summing the column totals or summing the row totals. So now we have what is called the contingency table, and from this we can figure out expected frequencies if the two variables are independent. If HO is true, if the null hypothesis is true, then what the expected frequencies will be. And the expected frequencies can be calculated with this formula. So E sub ij represents the expected frequency of row I and column j. So you take the row total T sub I dot, multiply by the corresponding column total T dot j, and then you divide by the grand total. And that gives us the expected frequency for each possible value. So now we have a contingency table of observed frequencies, and correspondingly we have a table of expected frequencies. So for each observed frequency we have a corresponding expected frequency. Expected frequencies being the frequencies you would expect if the null hypothesis is true. And once again, all expected frequencies must be greater than or equal to 5 for the test to be valid. If this is not so, then you have to increase the sample size or maybe combine the values of some of the rows and some of the columns. Now let's look at the test statistic. The test statistic is you take the observed frequency from the contingency table, subtract the expected frequency from the expected frequency table, so f sub ij minus e sub ij, square it and divide by the corresponding expected frequency e sub ij. You do that for all the cells and sum them all. So then you get chi-squared sub calc, that's our chi-squared test statistic, and the corresponding degrees of freedom is n minus 1, the number of rows minus 1, times the number of columns minus 1, or m minus 1. This chi-squared test statistic can be used in the chi-squared dist function to find the p-value. chi-sq.dist.rt, the degrees of freedom, of course, is this. Based on the p-value, then we can make a conclusion.